Welcome back to Lecture 1 of Organic Contaminants. We're still dealing with solubility, partitioning between the non-aqueous phase liquid and the groundwater. NAPLs are almost always a mixture of organic chemicals. When an NAPL is in contact with water, the concentration of each individual species in water is equal to the mole fraction of that species in the NAPL times the solubility of that pure phase organic. So the aqueous concentration depends on the ideality of the NAPL. Raoult's law really applies to ideal solutions. And it requires us to determine the mole fraction, which requires us to determine the total number of moles present in the NAPL. To do that, we really have to know all the components in the NAPL and how much of each component is present. That's clearly impossible for many NAPLs, like gasoline, so we have to come up with various approximations. And again, remember that for a few chemicals, their solubility needs to be keyed if they're solids or gases. Raoult's law does appear to work. A study by Broham and Feenstra found that Raoult's law does apply for NAPLs, at least when the NAPL is formed of similar chemicals like chlorinated solvents or gasoline hydrocarbons. So our proposal is to use Raoult's law as a first-order estimate. Here's a question we can perhaps consider then. Why is benzene typically found at concentrations less than 40 milligrams per liter in groundwater within gasoline source areas? That is, where there are NAPL composed of gasoline. Gasoline is typically 1 to 3% benzene. We know benzene's aqueous solubility is about 1,800 milligrams per liter. So why don't we see groundwater that has 1,800 milligrams per liter of benzene in it? Well, it's because Raoult's law does apply. The concentration of I, or in this case benzene, is equal to the mole fraction of benzene in the NAPL times its pure phase aqueous solubility, 1,800. Now in this case, we'll estimate the mole fraction of benzene in gasoline to be equivalent to its volume concentration, 1 to 3%. So the concentration of benzene in water is equal to the mole fraction of benzene in gasoline times 1780, its solubility. That would leave us with benzene concentrations of 18 to 50 milligrams per liter. So rather than seeing benzene in groundwater at its reported solubility, we see it at about the solubility we could predict from Raoult's law. Another reason why we might not see groundwater, even in a source zone, fully saturated with each of the NAPL components is the following. Here we have a porous media with a water table, and below the water table we have residual hydrocarbons, residual gasoline. If we look in detail at the flow lines as we pump this monitoring well, we see that some flow lines really don't contact the NAPL very well. Other flow lines have good contact, and those flow lines may in fact become saturated with the NAPL components. Again, that one isn't too bad. That one isn't too good. Not too good. Not bad. There's a good one. Not too good. Nothing. 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 Remember, when we sample a fully screened well like this, we're getting some average concentration over that interval. So very few of those flow lines, in fact, come in good contact with an NAPL, and therefore very few of those flow lines should be saturated with respect to the NAPL. NAPLs are distributed in very irregular fashions. This is a picture of a DNAPL spilled at Borden, and the distribution in various horizontal slices as we go down. You can see the NAPL isn't the same everywhere. So this combination of complex flow lines and integration within the monitoring well means that we probably don't see the NAPL saturated value that we should expect. Just because you don't see the NAPL saturated value doesn't mean the NAPL is not present. In fact, a typical rule of thumb is if you're finding concentrations within about 1% to 5% of the Raoult's law calculated solubility, there's probably a NAPL present. So Again, we have this problem of flow lines not all contacting NAPLs, long screens integrate. Another aspect is kinetic dissolution. We're assuming equilibrium so far in our treatment, but we know that when water moves quickly past a NAPL, it may not attain equilibrium. It may not reside close to the NAPL long enough to maintain equilibrium. So in some cases, we might want to describe the dissolution process as a kinetic process, if we can determine the kinetic factors. So again, the scale really matters. We might find water attaining saturation in small microcosm experiments, but at field sites, rarely do we find things being so simple. So that's all for solubility and NAPL dissolution. We'll move on to other partitioning in the next lecture. Thank you.